to neutrino. But as I already mentioned, I think I did mention this when discussing just at the end of the weak interaction lectures. I told you about the discovery of the neutrino mass through oscillations. I will take up that a little bit in more detail, hopefully, after finishing the standard model now. So, therefore, neutrino does have a mass, although it is a very tiny mass, but it is mass. Mass is definitely there. So, we have to bring in mass, and that problem is not yet completely solved, although there are theoretical ideas about how to bring in neutrino mass. Theoreticians are working on it. We do not know which particular way will come out right, and in getting the correct way, we might discover something much beyond the standard model also. That is the reason why the neutrino field is very, very important. In particular, that is the reason for INO. INO's importance. INO, the India-based neutrino observatory, which will come up in Thane district, is very important, because neutrino is going to be a very important window to go beyond the standard model. Otherwise, the standard model has proved remarkably successful and robust. Every data, every experimental datum which comes from continues to come from LHC Large Hadron Collider, all the data continue to, theoreticians are able to calculate everything in standard model and check with what comes out of the experiment, and they are in perfect agreement, except for this one signal that the neutrino mass is not 0. That is the importance of neutrino mass, because we have found a way to break the standard model and thus go beyond the standard model. Because in science we do not stop after having, there is no end to it, because after having reached one peak, we go and try to climb the next mountain, and now there is a way open for climbing the next mountain beyond the standard model. Neutrino has provided that. Okay, shall I start now?
Yeah.
So, let me add the fermionic terms to the SU2 cross U1 Lagrangian and try to construct the complete SU2 cross U1 theory. Pardon me? Okay, sure. By the way, this table is valid not only for the first generation which I have indicated here, for all the 3 generations of the quarks and leptons. Please remember that. I am now going to include all the generations. So, we get the complete SU2 cross U1 Lagrangian now. First, the gauge field, pure gauge field terms. Remember, there are 3 W gauge bosons, W1, W2, W3, square of that, and then one U1 gauge boson, which we called B. square of that. Then the fermionic terms, they are all Dirac part of the Lagrangian. So, as I said, in the electroweak theory, the left-handed and the right-handed parts of the fermions behave differently, and the left-handed parts are doublets, which I called QL. Remember, I just rubbed off. QL is UL DL, gamma mu, and then the covariant derivative. This is a doublet, so it interacts with W mu with this thing Ig tau by 2. Remember, this we did even for the phi, similar thing we did. So, exactly same thing for the, because phi also was a doublet. Just go back to the earlier SU2 cross U1 Lagrangian, and such a covariant derivative came when differentiating phi. So, when differentiating QL also same thing will happen, and also the U1 part, and that will come with a hypercharge. Oh, I forgot, I should have kept this hypercharge table. Remember, the hypercharge of the QL was 1/6, that is 1/6 will come into B mu. So, this is the covariant derivative. You should know how to form the covariant derivative. It is d mu plus I times the coupling constant times the whatever is the gauge field, but the correct hypercharge has to be put. Here the correct isospin comes because of the Pauli spin matrix tau into QL. Then the right-handed parts UR bar gamma mu. The right-handed parts do not have the W interaction, that is the thing, and the only the U1 interaction. And the hypercharge was just 2/3 because it is equal to the charge, since I3 is 0, as I already mentioned. I G prime B mu UR. Similarly, D term. I do not know whether it is minus or plus, everywhere let us put plus. These signs I am not very sure, you can take it from books. I dr bar gamma mu. Only one sign is correct, but I just do not remember the signs properly. D mu. This also does not have the W interaction, and the hypercharge was minus 1/3, because it is the same as charge, ordinary charge, electric charge, dr. Then the leptons, first the lepton doublet, I LL bar gamma mu d mu I G tau by 2 dotted with W mu vector minus I G prime, hypercharge I think was half or minus half, maybe it was minus half, I G prime B mu LL. Then the right-handed thing, only right-handed electron, I E bar gamma mu d mu. The right-handed part has only the B interaction, and putting the correct hypercharge, which is perhaps minus 1 or something. That is all for the fermions. These are the fermionic kinetic energy terms. Putting covariant fermionic kinetic energy terms plus their interactions with the gauge bosons, they come together. The kinetic energy always comes with the interaction with the gauge field. Then the phi field, the scalar. This part is same as what we already wrote down before I talked about the fermions. Although it is written as mod squared, it is not as simple as that. We have to take the Hermitian conjugate of this whole thing into itself explicitly. It is not the complex conjugate, just the Hermitian conjugate times this minus the potential term lambda 5 power 4 term. Then the Yukawa terms which we have just now discussed, which can be added, minus HU QL bar phi C UR plus HD QL bar phi DR plus HE LL bar phi into ER plus Hermitian conjugate. This is for one generation. Now I have to generalize this to 3 generations. Now I am going to introduce a notation. I will continue to call the generations as 1 to 3. So I will introduce a notation. So I will change here itself maybe. Please change here itself. I will introduce N L N L N summed over 1, 2, 3. N equal to 1 is the lightest generation made of U and D quark. N equal to 2 will correspond to C and S quarks. N equal to 3 corresponds to T and B quarks. That is my notation. I will follow that notation hereafter. So please change this into E. Put that N there. N index. N is the generation index. Similarly for leptons, N equal to 1 is the electron generation, N equal to 2 is the muonic generation, and N equal to 3 is the tau generation. So NL, NL, NR. So here also I should have written. Phi, there is no change. Now here what do we do? Here also I can put N equal to the same thing, similarly put N everywhere, but here there is an additional possibility. And remember the the SU2 and U1 quantum numbers, SU2 and the hypercharges are the same for all the generations, and hence in forming this interaction, Yukawa interaction, there can be intergenerational mixing. For instance, this could be first generation, this could be second generation, or first generation and third generation. So I have to introduce more terms. The intergenerational mixing comes in the Yukawa term. That is the complication of weak interaction theory. The Yukawa coupling, so this replace replaced by it will be now summation over 2 indices m and n, again going from 1 to 3. And Yukawa coupling, now I will introduce a different notation, gamma Yukawa coupling for the u sector, the up sector, that will be q bar ml phi c u nr. The diagonal parts of it. So, this is a 3 by 3 matrix, you can see, but the diagonal elements are the same as before. I mean, if I had put only diagonal terms here, but off diagonal elements are allowed. So, this is the more general Yukawa coupling. Similarly, for the down quark sector, q bar ml phi into dnr, and the electronic sector, I mean the electronic sector, gamma e mn ll ml phi e nr plus hc Hermitian conjugate. So, that is the Yukawa coupling. Yukawa coupling can mix generations. Can mix the generations. I mean, here all the generations stand apart, there is no coupling by intergenerational coupling, but Yukawa coupling has intergenerational couplings. And remember, the mass terms came from this. So, similarly, replacing these phi's by their vacuum expectation value, you will get mass terms which are non-diagonal. So, mass terms are non-diagonal in generation space. But they can all be diagonalized, and once you diagonalize and get the diagonal contributions, there will be so these u's, for instance, this is u1, u2, u3, which corresponds to remember, maybe somewhere I should have written it down. Maybe this is the right place to write. So, generation number 1, that is u d for the quark sector. This for L and L, and you can put the right handed thing also separately, but for simplicity let me write like that. And then what is it, nu E and E, that is 1. You can expand it into the left-handed doublet and the right-handed singlet if you like. That will be the correct thing. Generation 2 will be this is n equal to 1. N equal to 2 will be C and S quarks, and here mu and mu. That is generation 2, and similarly generation 3 can be written down. The heaviest generation, namely top quark and B quark, correspondingly TLBL and TRBR as singlets, and here tau. So, this is what I should write now. The notation here n equal to 1, 2, 3 correspond to these things. When u1 d1 means this, u2 d2 means this, u3 d3 means this. That is the meaning of the notation. And in the generation space it is non-diagonal. So when you diagonal, so I mean matrix, now the mass becomes mass matrix. You diagonalize the masses, so you will get to the diagonal eigenvalues. Those will be the masses, and the corresponding eigenstates will be linear combinations of the original generations. Okay, these generations, certain linear combinations which have coefficients which are determined by the Yukawa matrices. So linear combinations of the three generations will come as the as the mass terms, in the mass terms. But remember, these fermions come here also as couplings for these W's. There they remain diagonal. So we have to write these diagonal, I mean these things in terms of these real eigenstates of the mass matrix. The eigenstates of the mass matrix will have to be, I mean these original states have to be written as linear combinations of those mass eigenstates. So the mixing will not be there in the mass matrix because we have diagonalized it. Then only we can understand what is mass. But then the mixing will reappear in the weak interaction. So the intergenerational mixing reappears in weak interaction. Once we diagonalize the mass matrices, there will be three mass matrices, one for the up type of quarks, another for down type of quarks, and another for the charged leptons, E mu tau. Once we diagonalize the mass matrices, the the mixing between the generations will enter through the charged current weak interaction. Neutral current weak interaction will not have that complication because of this. Let me write down charged current weak interaction first. There again I have to introduce some notation. Remember, charged current weak interaction was B minus A, and then D will come here, but now I will put all of them together as one capital D. Now the notation is capital D stands for, where do I write it? Yeah, D, S and B quarks. Similarly, U here, which stands for U, C and T. So this is 3 by 3 generation. In the generation it's a column vector, it's a column vector. I'm sorry, this is U bar, right? But now what I am saying is this is the original thing, this is nothing but the original thing. I mean U bar will be connected to D and C bar will be connected to S and so on. But now because there is, we have got linear combinations which diagonalize the mass matrix, these original states will be written in terms of those eigenstates and they will become mixed through this matrix. So let me introduce. Yeah, unitary matrix VU dagger and VD. What are these? VD, V is a 3 by 3 unit matrix, this is another 3 by 3 matrix. It is this unitary matrix which diagonalizes the down quark mass sector, down quark mass matrix, and this VU is the unitary matrix which diagonalizes the up quark mass matrix, and it comes because of this bar, this will come as a dagger and this, and so what comes is not these diagonalizing matrices themselves, but a combination of them, and that combination I will call V. So the charged current weak interaction therefore is U bar gamma mu 1 minus gamma phi into a 3 by 3 unitary matrix. The charge current weak interaction is this into W mu. So let us write plus Hermitian conjugate. That is the charge current weak interaction apart from coupling constant. So let us write down the full form. So V into D into W mu plus Hermitian conjugate. And here W will come, here W dagger will come. If it is W plus gauge boson, weak boson, it will be W minus here, that is all. So that is the charged current weak interaction. So charged current weak interaction appears which has intergenerational mixing. This V is an important matrix called CKM matrix. CKM matrix. C refers to Cabibbo, K refers to Kobayashi, and M refers to Moscow. There is an interesting story connected with this. Cabibbo introduced it purely on the basis of weak interaction phenomenology, when only the this quark had not been seen, but at least the Strangeness quantum number had been identified. SU3, the old SU3 had come, and on that basis he showed that there has to be some extra, apart from that was the days when there was a current interaction, not even W boson standard model had not come. So he had shown that there is another parameter which is coming called the Cabibbo mixing parameter, purely on phenomenological grounds, on the basis of empirical weak interaction data, he introduced it. And he himself once quarks came, he introduced it as a mixing between two generations, D and S. Then later, Kobayashi and Moscow generalized it into 3 generations. Even before the 3 generations were experimentally discovered, Kobayashi and Moscow had the foresight to ask the question how to introduce CP violation. Remember, I had discussed CP violation long ago when weak interactions were discussed. To introduce CP violation, they showed that it can be done if this matrix is a 3 by 3 matrix. Minimum number of generations in order to introduce CP violation was 3. So they predicted that there have to be 3 generations when only 1.5 generations had been seen. Only UDS 3 quarks had, 3 quarks had been seen. Quarks had not been seen, but the guess was that there were 3 quarks, UDS, only 1.5 generation. Then successively B quark was seen, and C quark was seen, B quark was seen, and T quark was seen. And CP violation also through this, essentially this matrix is a unitary matrix, not an orthogonal matrix, more generally, because this is all quantum mechanics, everything can be complex, and it can be unitary matrix, which can be written as orthogonal matrix, but you put some phases. And they showed that at least one phase, to get one phase, you need at least 3 generations. That was their theorem. It was a very simple calculation. I can do it in 10 minutes, maybe sometime in one of the later lectures I will do that. So that is the story of the CKM matrix. And then the CP violation seen in the B quark bound states, all these to a certain extent I have already talked about, namely the B, you remember the B meson I talked about, the heavy quarks and their bound states, capital B, which contains at least one B quark. And there the CP violation was studied. It was a very long program, and they established that the CP violation is exactly as would come from this CKM matrix. So Nobel Prize was given. Again, Nobel Prize fellows made a mistake by omitting Kabibo, and they gave only to Kobayashi and Moskawa. But the matrix is called CKM matrix. That is the CKM matrix. Now, I will not repeat it for the neutrino sector. I am going to do neutrino sector a little bit more in detail after finishing the standard model. Similar, more or less similar thing goes through for the neutrino sector, and there will be a mixing between the neutrinos, and it is that mixing which leads to neutrino oscillations, and it is through oscillations that the neutrino mass was discovered. That is the importance of the mixing in the leptonic sector. And in the hadronic sector, quark sector, the mixing is very important. It is because of this mixing, the heavier quarks all decay, leaving the present day universe to be made up of only the lighter quarks, U and D. Because otherwise all these quarks would be constituents of all our nuclei. Physics would have been, physics and even chemistry, everything, life would have been very, very, very different. But fortunately only U, D and the electron and the neutrinos survived to be constituents of the matter in the universe because of this mixing. It is because of this mixing now, because remember, because of the CKM matrix, now the C quark, otherwise the C quark could have decayed only into C, but but now C quark can decay into U and D, and the T would have remained decaying only to B. Only the charge current weak interaction only connects upper and lower and up, right? It does not connect. But now the charge current connects the intergenerational mixing. So C quark, since it is heavy, all the particles containing C quark would decay into this. Similarly, T. So finally, only the U and D being the lightest quarks, only the proton and neutron remain. That is the importance of the CKM mixing. So this more or less completes the electroweak theory. So combining this with the QCD, I will construct the full standard model. But before that, I will spend some time. Whatever I discussed now looks very, very technical. It involves knowing about Dirac equation, Dirac matrices, gamma matrices, and so on. But now I will try to answer some simple questions in a simple way. So that is what I want to do now.
Just before that,
yeah.
When we have this mass matrix,
yeah.
What do we interpret the eigenvalues of this mass matrix as? Are they?
They are the masses. Yeah, they are the masses. The phi 0 vacuum expectation value times the top left eigenvalue will be the mass of the U quark, and the next will be the.
Since eigenvector is a mixed thing of all the quarks.
Yeah.
So whose mass is?
It is eigenvector. Eigenvector are the genuine particles. Okay, because they have the well-defined masses. A particle should have a well-defined mass, right?
So that means that the linear combination of these quarks is like another particle.
No, that is not another particle. The way I am interpreting is only the eigenvectors are the particles, and the mixing comes here, and the mixing we explicitly take care of. So what comes in U and D are the eigenvectors. That is why the mixing comes in the charged current weak interaction.
Yeah, but those eigenvectors
are mixtures of the original particles, which we no longer consider as particles. They are they are the starting things, but it is the linear combinations which turn out to be the real particles. So, since in the weak interaction Lagrangian, it is the original particles which came, and the original particles have to be written as linear combinations of these newer eigenparticles, I mean well defined massive mass particles, mass eigenstates. It is the mass eigenstates which I would call a particle. And so, what comes here are the mass, not the mass eigenstates.
But when we do an experiment, we get the mass of some quark.
Yeah, definitely. Therefore, it is an mass eigenstates only which we see. We don't see the mixture of electron, muon, and tau. They have different masses. But your question is very important, because what happens in the neutrino sector? There the masses are there, and the masses are so nearby, you cannot say that an experiment produces only one type of neutrino. It will be a linear combination always. That is why the neutrino oscillation takes place. The answer to your question really is a neutrino oscillation. Since you cannot determine energies in experiments to a fraction of an electron volt, and the masses of the 3 neutrinos you will see differ only by fraction of an electron volt, what is experimentally produced will not remain as a mass eigenstate, it will oscillate between the mass eigenstates. In contrast to electron, muon, and tau are the three in the quark sector, where it is the mass eigenstates which are experimentally produced. Whereas in the neutrino sector, it is not the mass eigenstates which are produced, but it is the linear combinations which are produced, and that is why they have to oscillate. That explains the neutrino oscillation. Yeah, this is a very subtle point. Even experts many times don't appreciate this subtle difference between neutrinos and other particles. For neutrinos, strictly speaking, there are also mass eigenstates I can define. I will define those mass eigenstates as the real neutrinos. Okay, but what happens is it is the linear combinations of the mass eigenstates which are sometimes called flavor eigenstates, which does not mean anything, which come in the interaction. So, it is that which is produced by experiment. The linear combinations of mass eigenstates, superpositions of mass eigenstates which are produced in any experiment which produces a neutrino, in contrast to every other particle. That is simply because the 3 mass eigenstates are so close by in mass, and the experimental uncertainties being as they are, you cannot distinguish between them. So, when you detection also, not only production, detection also.
Whereas for other leptons and quarks, it is the mass eigenstates that are produced in the experiment.
Yeah, yeah. For neutrinos, the situation is very different. It is the linear combinations of the mass eigenstates which are produced in experiment and detected in experiment. And that is why the neutrino oscillation, there are no oscillations for other particles, because it is the same similar kind of matrix. Here it is called CKA matrix. In the leptonic sector, it is called PMNS matrix. I will discuss it later. PMNS, what are the names? I always forget the names. There are 4 guys' names there. There also is the 3×3 matrix. Situation is very analogous so far, but the mass matrix for the neutrinos being almost degenerate, the different mass eigenstates are not separately produced. It's only because of the experimental situation the difference comes between neutrinos and all other particles. Okay?
Yeah. Thanks.
Yeah. One more thing I forgot to mention at this stage, I should mention. Of course, when you consider the mixing and so on, you remember the W plus, W minus, and desert boson came, and photon came, and so there are not only charged current weak interaction, there is neutral current weak interaction and electromagnetic interaction. Now, how do they look like? Remember, these look like, forget about the gamma matrices, neutral current weak interaction will look like, because U goes to only U. So, U bar U. Neutral current weak interaction is not B minus A, but some gamma matrices. So, when you have this, for instance, what will come? It will come as Vu. I am using Vu, and here it is Vu dagger. Instead of two different V's, the same U's comes. So by unitarity, it is 1. So no intergenerational mixing will happen in neutral current weak interaction, because neutral current weak interaction is diagonal in the flavor space, and so even this unitary transformation kills each other. So it is only U bar and some gamma matrix times U. Similarly for electromagnetism also is only diagonal. U bar U, D bar D. U bar U will come with the charge 2/3 into U bar gamma mu U, and minus 1/3 D bar gamma mu D. Similarly for electron. Okay. So here this is also electromagnetism also, U bar U. Similar, no mixing for neutral current weak interaction and electromagnetism, only for charged current. CK matrix comes only there. That is one point which I forgot to mention. Okay. So let me now ask some simple questions and give the answers in a simple way without going through all Diracology, gamma matrices and gamma phi and so on. I think I will keep this for the time being. There are still some more things to be said here. One more notational clarification I think I have to make. See, this kind of concise notation hides many things. Remember, Q is a Dirac particle, Dirac field, a 4-component Dirac field, and that is automatically contained with this gamma mu matrix sandwiches those a Dirac spinor and its adjoint spinor, same for all these things. And in addition, here remember tau is a 2/2 matrix, that is a different space. This is a 4/4 space, there is a 2/2 space. So that is taken care of by Q being U and D. So that 2/2 matrix gets sandwiched between those two components. So if you want to write fully, you have to write the Dirac. So in addition to these symbols, you have to write the Dirac index and the SU2 index, which we don't do. Okay. So please remember that it's a concise notation, and because this becomes even more important when I write the full standard model. The only thing which we are writing explicitly is the generation index, because I wanted to focus on the generational mixing. Everything else is supposed to be understood. And also another thing, since this is a 2/2 matrix, everything else has to be a 2/2 matrix. So this is a 2/2 unit matrix, and there is a 2/2 unit matrix here also, similar thing. That point I had made already. So let me now come to what I wanted to say here. Some questions and elementary answers for them. One, why does electron, for instance, or even the quark, electron require Higgs mechanism? Because that is what we found. Of course, we have proved it mathematically, but I want to give a physical interpretation for that. Require Higgs mechanism for mass. Electron, as I said, has two parts, left-handed and right-handed. And EL and ER have different generalized charges. They have different gauge charges. EL is a doublet and ER is a singlet. Similarly, the Y quantum number also is different. Now, if mass is different from 0 for the electron, electron can travel with speed, will travel with speed less than c, is always less than c. It will never reach c, it will always be less than c by principles of relativity, and hence you can think of traveling even faster than that v, below c but faster than v. And in your frame, what was EL will look like ER, because remember that EL and ER are the directions of spin. The spin was pointing this way, but you are traveling faster than that. Actually, what happens is the direction of momentum gets reversed. In your frame, when you are traveling with velocity, with a velocity larger than the velocity of that electron, in your frame, what was EL will look like ER and what was ER will look like EL. So, you cannot consistently maintain an invariant meaning for EL and ER if mass is different from 0. That is why mass has to be equal to 0. If mass is equal to 0, electron always travels with velocity c, you cannot overtake it. So, what remains left-handed will remain left-handed, and similarly what is right-handed will remain right-handed. So, that is the reason. By traveling faster than the particle, EL will look like ER. So, M not equal to 0 is not possible. So mass is not possible. That is the reason why mass could not be generated in the original standard model before symmetry breaking. In symmetry breaking, we are introducing Higgs. So, how Higgs solves the problem? Higgs, what is Higgs? We give a vacuum expectation value. It is an all pervading field, scalar field, all pervading field, and so it is something like a field existing everywhere. And so, an electron interacts with that field. And it is that all pervading Higgs field supplies the required gauge charge. And hence EL and although the original EL and ER had different charges, but in the presence of the Higgs field that is no longer true, and so what looks like EL can become ER, and so mass becomes possible. That is how Higgs solves the problem of the mass by interacting with EL and ER and supplies the missing gauge charge and provides mass. So, that is the explanation of the Higgs mechanism, a sort of qualitative explanation for the mass problem. So, second question is why does this not happen for neutrino? That is because nu r has been banished. Because nu r has been banished from standard model. So, the Higgs field does not affect or does not interact and does not affect the neutrino at all. and neutrino remains massless. I mean, that is my explanation, which we already know, because remember I could write the Yukawa coupling for the EL getting ER, and this is the field, and that field we replaced by the vacuum expectation value, just a constant which exists everywhere. We do not feel it, and we know it exists because electron has a mass. Okay. So, that constant field which exists everywhere converts EL into ER, but since nu r does not exist, this does not happen. That is why the neutrino remains massless. Now, I have two other questions which also have some simple answers. I think I will have to rub off. The third question I have is, this is not related to neutrino at all, related to photon. How does this question you should have asked, and so you might already know the answer. How does photon get away with with the two spin states? Remember, photon has spin 1 and the directions have spin one in the direction of motion, another perpendicular to it. These are the two spin states. That is for the particle point of view. But photon is also an electromagnetic wave. From the wave point of view, these are the two transverse polarizations. There is no longitudinal polarization. Two transverse polarizations are equivalent to the two spin directions. Spin in the, see, spin is like this. Photon is going in this way, spin is like this. So, in some sense it is transverse motion, you can say. Spin is transverse motion. It is more like circular polarization, and by taking the left and right circular polarization, linear combinations of them, you can have linear polarizations also, right. That is the original linear polarization of the light wave. So, the two linear polarizations which are transverse, there is no longitudinal polarization, and from the once you quantize it, you will get only two spin states. But photon is a spin 1 particle, and in angular momentum theory, any spin 1 object should have 3 spin directions. How does photon get away with just 2 spin directions? I am sure you would have asked this question and got the answer. If anybody knows the answer, does anybody know the answer? I am sure some of you already. Yeah.
It doesn't have a rest frame.
Correct. That is the answer. See, spin, internal spin of a particle is defined as the angular momentum in its rest frame. Then you do the angular momentum algebra, you get this result. If spin is j, there are 2j plus 1 m values, the directions of spin. But since photon cannot have a rest frame, this cannot be done. This theorem is not valid. For photon, the correct group is not the full rotation group, but the, so I think Euclidean group, E2 or E3, I do not remember, and there you find that 2 spin states are allowed, and that is why photon gets away with the 2 spin states, because photon cannot be brought to rest. Fourth question, it is not a question, it is just a point which I already made, but I want to repeat it. In Higgs mechanism, the massless Nambu-Goldstone boson is eaten up, and it becomes the longitudinal component of the gauge boson, and so the number of spin states is restored to 3. because in the Higgs mechanism the particle, the gauge boson becomes massive, and what happens is the Nambu-Goldstone boson becomes the longitudinal component of the gauge boson. That is how it becomes a regular spin 3 massive particle. So that is all the point. The extra component is supplied by the Nambu-Goldstone boson. So that is all. If you have any question on these simple remarks, you can ask me. We are more or less complete. Electroweak theory is more or less complete. Now let me just make it a complete standard model. It is very easy now. We have to add the QCD part. QCD anyway I am not going to discuss in detail, that is much harder, so I am not going to do it in this course. So let us add QCD. Remember QCD has its origin in the discovery of asymptotic freedom, namely the quarks as seen in deep inelastic scattering, namely at very high energies, correspondingly very short momentum, very short momentum corresponds to long distance. So either large distance or short momentum, I mean what shall I say, short distance or large momentum, large asymptotic momenta, that is why it is called asymptotic freedom. When the momenta and energies of the particle quarks become very large, the quarks behave like free particles, that is why it is called asymptotic freedom. And it was found out that no quantum field theory has asymptotic freedom except a non-abelian gauge theory. So you need non-abelian gauge theory for that also, just as electroweak theory needed non-abelian gauge theory, at least partly, the SU2 part. So one degree of freedom was already there. The color degree of freedom was already discovered when I discussed the quark model. In order to satisfy the Fermi-Dirac statistics for the 3 quarks in the ground state, basically the ground state, but the first excited state, they spin 3 to delta and so on, the decimate states of SU3, in particular delta plus I discussed. And it required an extra quantum number in which the wave function is antisymmetric, satisfying Fermi-Dirac statistic. That extra quantum number was called quark, and now you form an SU3 symmetry on these 3 variables, the 3 color degrees of freedom. And so SU3 color is color theory, SU3 color gauge theory is quantum chromodynamics, motivated by the discovery of asymptotic freedom. So the Lagrangian of QCD is nothing but -1/4 the gauge, and the gauge bosons of the SU3, there should be 8, since SU3 has 8 generators, so 8 gauge bosons, and they are called gluons, and the gluonic field is G mu. Here I goes over 1 to 8, and then this nonlinear term Fij are the structure constants of the SU3 group. So QCD, how does it come? Asymptotic freedom leads to QCD, which is actually SU3 in color space. QCD is nothing but SU3 in color space. So Ijk go over 1 to 8, because G, there are 8 gluons, so the 8-dimensional representation of SU3, and this is the structure constants of the generators. Just go back to my discussion of SU3 in the context of original SU3. That original SU3 was in a different space, the UDS, the light quark space. That is how the SU3 came. But remember, that is not a fundamental symmetry. The fundamental symmetry is the color symmetry, which was discovered much, much later, but the mathematics is the same as what we had already discussed. G mu G I G nu J. No, I think I am doing something wrong. J K. J and K are summed over, but I remains, so everywhere I remains. And so this into another similar quantity with I multiplies, that is the gluonic field Lagrangian, and then the quark Lagrangian. So here again I am introducing another notation now, sorry. Maybe I will introduce alpha to distinguish from this I. Alpha equal to, there are 6 quarks, right? Each quark behaves in the same way in this as far as the QCD Lagrangian is concerned. Q alpha bar I gamma mu d mu. The covariant derivative now will involve the Gell-Mann lambda matrices. Gell-Mann lambda matrices I had introduced in terms of the original SU3, but the mathematics is the same. So, the same Gell-Mann matrices now in color space, lambda j over 2 G mu j minus m. Here, remember, there is no complication of B minus A theory separating QL and QR, and so I can write down a mass term very easily, minus m. If it is a QCD Lagrangian, I can simply write down a mass term for each quark, no problem. So, this is all the QCD Lagrangian is. Maybe I will say a little bit about this asymptotic freedom. Remember this, there is a quadratic term here, linear term. So, when you multiply it by itself, there is this, the gluons generally denoted like a spring, whereas the other gauge bosons like photon, they are denoted like this wavy line. So, there is a cubic term and a quartic term, and then of course, there is this quark gluon term, that is the coupling G here, this is G squared, I am sorry, this is the 4th order term, quartic term. So, this is 2nd order and G squared already in the coupling itself. So, these are the couplings, and it is this coupling which converts the theory into an asymptotically free theory. The cubic gluonic coupling is responsible for turning the theory into asymptotically free theory. Unfortunately, I cannot go over the theory of asymptotic freedom, that requires working out renormalization group, which comes only under advanced field theory. Even elementary field theory we have not done fully. So, advanced field theory is needed, but the result is the following. The result is, through renormalization group, what is called renormalization group, even renormalization we have not done, through renormalization group, the coupling constant becomes a function of the momentum transfer in the interaction or the energy, and basically the energy or momentum involved in the process. So, RG turns all the couplings, all the parameters, even mass parameter, etc., becomes a function of the energy or momentum at which you are measuring it. Okay. And then you find the following result. Whereas, let me contrast QED and QCD. In QED, this is QED. And this is let us say the momentum transfer, Q squared. For small momentum transferred, you can take QED coupling constant small, the Fein-Scheiser constant is only 1/137, and it becomes a run. This is called a running coupling constant, and the running makes it larger. So, this is QED, the coupling constant is called the Fein-Scheiser constant. alpha. Alpha as a function of q squared really goes to, so for very large coupling constants QED is very difficult to deal with. Whereas here in QCD what they discovered was through renormalization group as a function of q squared it is just opposite behavior. Let me call it alpha QCD or alpha strong, and alpha strong is g squared, the strong coupling constant divided by 4 pi, exactly like this fine sector constant is E squared by 4 pi. 4 pi H cross C, but H cross and C we are always putting 1. So, this 1 over 137 is here, but then it becomes very large here, but here it is the other way. So, this is where they did the deep inelastic scattering experiments by allowing high energy electrons colliding on proton, where it is this region, and in this region the quark coupling constants are small, that is why they behave like free particles. That is the discovery of asymptotic freedom, and it is valid only for non-abelian gauge theory like QCD. So, large momentum or short distance, because remember there is an inverse relationship between length scale and the momentum scale. So, large momentum corresponds to short distances. At short distances inside the nucleon, the quarks behave like free particles, but if you try to extract the quarks, then we have to send the quarks to large distances between themselves, and large distance corresponds to this. Here the coupling constant blows up, and so you can say this is the region of asymptotic freedom, and this is called infrared slavery. The quarks are confined by very strong potential because the coupling constant becomes very large. So, that is called quark confinement or color confinement. This I already mentioned in my very first lecture. That is the reason why quarks and gluons are not seen as free particles, because we try to extract the quarks from proton, we have to go to large distance. At large distance, the coupling constant blows up, and the coupling constant becomes very large. Whether it blows up or not, we do not know. See, in contrast to here, where perturbation theory is valid, asymptotic freedom can be proved, but the infrared slavery cannot be proved. That is why quark confinement not yet proved. But it is conjectured to be true, and many people think that it has been proved in lattice gauge theory and so on, but I do not believe that that is proved. So, it is contained in the Yang-Mills field equations. Yang-Mills field equations are the field equations of motion derivable from this Lagrangian. By using the Euler Lagrange equation, you will get the Yang-Mills field equations. So, it is this which leads to color confinement. That is what is believed, but it is not yet proved. So, that is all I will say about QCD. Now, I will combine this QCD Lagrangian and the electroweak Lagrangian suitably and write down the standard model, which I discussed in my first lecture. Okay, that is what I will do in my next lecture. So, if you have any questions, you can ask me. So, now we are ready to discuss the full standard model. Okay.
Yes.
My lectures on the building up of the standard model contains some details, not full, some details of this renormalization group, how it leads to the momentum dependent or the running coupling constant so called, and how, some more details are given there, but even that is not a complete discussion of renormalization group. Okay, if there are any questions, you can ask me. Otherwise, we will meet next week.
Yeah, so we will meet next Saturday.
Next Saturday. Okay.
Thank you. Thank you, sir.
Thank you all.
பண்ணிட்டு நான் உங்களுக்கு லிங்க் அனுப்பி விடுறேன். கொஞ்சம் டைம்